Hello and welcome. In this video we will talk about the life cycle assessment of wind turbines. And I will present this topic together with my colleague Hanna Neumann. And what will we talk about when we discuss life cycle assessment? First of all, we need to know what is life cycle assessment and how we can do that. And then we will see some examples of life cycle assessment of wind turbines, because different researchers already have done that. And then we will have a comparison of wind turbines to other electricity generation facilities. Hanna, what is a life cycle assessment?
A life cycle assessment assesses in a systematic way the environmental aspects and impacts of product systems, from raw material acquisition to final disposal, always in accordance with the stated goal and scope. So there are some methodologies for carrying out a life cycle assessment. These are described in ISO 14040 and in ISO 14044. And there's also software available that can be used in order to carry out a life cycle assessment. A life cycle assessment consists of 4 phases. The first phase is the definition of the goal and scope. So first of all, the system boundary has to be defined. And afterwards, a functional unit has to be defined. For example, the production of 1 kilowatt-hour of electricity by a wind energy plant.
And in the second phase, we will then talk about the life cycle inventory analysis, the LCI, the inventory of the input and output data. So we start with collecting all the data that is necessary to achieve the objectives of an investigation, of a study we would like to perform. And as an example for input data, that is, for example, all the materials used for the production of the wind turbine. And an example for output data is the material that we can gain by recycling processes.
So the third step is the life cycle impact assessment. This provides additional information to support the assessment of the cycle inventory results of a product system. For example, here the greenhouse gas emissions are examined, or the cumulative energy demand, or the acidification.
And then we conclude with the fourth phase, the evaluation. So we take the results from the second and third step that are now discussed and summarized in accordance with the objectives and the study framework as a basis for conclusions, recommendations, and decision-making aids. The results are based on a relative approach. That means we refer to, for example, a kilowatt-hour produced electricity, and the results indicate then potential environmental effects.
On this slide, you can see a summary of the definition of a life cycle assessment. First, we have the goal and scope definition. Afterwards, the inventory analysis follows, followed by the impact assessment. And after that, we do the interpretation of the results. On the right side of the graph, you can see the direct applications that life cycle assessments are used for. For example, for product development and improvement, for strategic planning, for public policy making, for marketing, or for other reasons.
And now let's have a look to the different studies, the life cycle assessment studies that already have been done. And there are several ones that already treated the topic of wind turbines from cradle to grave. And for example, in the study of Haapala and Prampreda, they come to the conclusion that environmental impacts are determined mainly by the material consumption, and there especially from steel. And Mendeca and Lombardi, for example, they have studied several LCA studies and emphasize particularly the importance of the upstream processes. So, for example, the raw material extraction, the production of the turbine itself, and the construction of the turbines or the wind farms. And when they are in operation, that or more or less can be neglected. There we don't have an impact so much anymore.
So here you can see an example of a system boundary. In the upper left corner you can see the raw materials. These materials are distributed by the suppliers and afterwards used to produce the wind energy plants. And in the next step is the transport and installation, followed by operation and maintenance. And during their lifetime the plants produce electric energy, and after the lifetime dismantling and transport follows. Part of the plants is then recycled and the rest is displaced to disposal. Here I want to present a study of a life cycle assessment of 2 onshore and 2 offshore wind energy plants. The functional unit of these studies is the production of 1 kilowatt-hour electricity. And the system boundary includes all wind power plant components from power station to distribution wiring. This table here shows that between 5 and 11 gram CO2 equivalent per kilowatt-hour are produced. And in comparison, coal produces 990 gram CO2 equivalent per kilowatt-hour and natural gas produces 530 grams CO2 equivalent per kilowatt-hour. And additionally, the table shows the energy payback time. The energy payback time is the amount of time that the system needs to run in order to produce the amount of energy equivalent to the primary energy consumed throughout its lifetime. The values therefore are between 5 and 11 months, thus in all cases lower than 1 year. And the offshore plants have a higher impact than the onshore plants, and this is mainly due to larger high-impact material requirement for capital infrastructure in case of the offshore plants. And this slide also belongs to the before presented study. Here the sensitivity of climate change impact is presented. The red bars at the left side show a reduction of CO2 emissions, and the blue bars at the right side show an increase of the CO2 emissions. And the sensitivity analysis takes into account a change of different assumptions. These are the steel recycling efficiency, the foundation recycling, the efficiency of the wind energy plant, the lifetime and the wind speed. And the change in the value of the CO2 emissions is then between -20 and +40%. Additionally, the study examines the contribution of the different life cycle stages of the 4 wind energy plants to their total climate change impact. The extraction and production of raw material contributes to more than 70 to 80% of the climate change impact. The rest is produced by production, installation, operation and dismantling. Thus, there is a great importance of material recycling at the end of life. This slide shows the results of another study. In this study, the ecological balance of the offshore wind farm Alpha Ventus is examined. The material balance is shown on the left. 73.2% of the material used is ferrous metal. 8.1% are non-ferrous metals, 5.9% are synthetic materials, and 12.7% are other materials. It is also interesting that the submarine cable is responsible for 80% of the non-ferrous metals. The graph on the right shows the cumulative energy requirement. Thus, the total energy that is consumed during the lifetime of the system is shown here. 78.4% of this energy is due to the manufacturing phase, 20.4% is due to the use phase, and 1.2% corresponds to the disposal phase. The energetic payback time in this study is also less than 1 year.
When we have a look once more to the study of Mendecca and Lombardi, there we see, for example, the assessment of the greenhouse gas emissions in gram CO2 per kilowatt-hour electricity produced. And there we see for the very small turbines of only a few kilowatt nominal power, it is larger than those that are in the megawatt class. There we see that the impact is just below even of 10 gram CO2 for a kilowatt hour. For example, when we compare those 10 grams to what a coal power plant is emitting with almost a kilogram or 1,000 gram, there we see how environmentally friendly wind turbines, for example, are. And they also have studied the accumulated energy demand, and there we see more or less the same when we look to the very small turbines of a few kilowatt. That is higher than that we have for the very large turbines in the megawatt class, but again decreasing from that side of view.
In this graph you can see the global warming potential over the nominal power in kilowatt. The CO2 emissions exponentially increase with increasing nominal power. And the power law behavior is mainly due to the nonlinear scaling factor existing in the amount of materials required for the construction of the turbines. In this graph here, the CO2 emissions per produced kilowatt-hour of electricity are shown over the nominal power in kilowatt. The CO2 emissions in kilowatt-hour decrease with increasing nominal power. Thus, bigger plants are more efficient than smaller plants.
And then we come to a study of Gibbon and Hertwig in the United States, and they investigated the impact of wind turbines and other renewable power technologies in comparison to the conventional power generation like coal power plants, gas power plants, or combined cycle power plants. And there we see in those bars that the material consumption, the material use, that is the highest we can imagine for wind turbines and also high for other renewable power systems. Especially the usage of iron and steel is dominating that. And we see in comparison to that, the coal power, gas power plants have a quite small amount of materials they need. And therefore we see how important it is that we are recycling the materials for wind turbines. Because that is the good side of renewable power systems. We not really use the material and then it's gone. We always can reuse it again when we need to construct new turbines. And then we see on the small dots on the graphic, that refers to the scale on the right side. There we see the cumulative energy demand in megajoule required for 1 kilowatt-hour electricity production. And there it's completely the opposite. There we see the impact of the renewables is almost zero. It's hardly to see even. And it's very high for the coal and gas power driven stations. That we will see later in another slide how drastic that difference really is.
In this graph here, the land use for the implementation of different technologies in the USA are compared. Coal power has the highest occupation due to mining. It lies between 17 and 26 square meters per megawatt hour per year. And wind energy in comparison is in the order of 200 square meters per kilowatt hour per year, thus a factor 85 to 130 lower than coal. Here we want to present you a study of a scenario of environmental impacts until the year 2050. This study is a global integrated LCA of long-term wide-scale implementation of electricity generation from renewable sources. And the scenario is based on the Blue Map scenario of the International Energy Agency until the year 2050. The Blue Map scenario is a scenario of implementation of renewable energies. And the study comes to the conclusion that under these circumstances, a doubling of electricity supply with stabilizing or even reducing pollution is possible. But on the other hand, 11 to 40 times more copper for photovoltaic systems is needed than in the reference scenario. And 6 to 14 times more iron for wind turbines is needed. But additionally, the study says that 2 years of current global copper production and 1 year of iron production will be enough to build a low-carbon energy system that can meet the global electricity demand in 2050.
And then we conclude what we have seen in this video. First, we have had an introduction on life cycle assessment and how we can do that. We have seen that there are several studies on LCA for wind turbines do exist. And in those studies, we have seen that the climate change impacts of wind turbines is significantly lower than those of most other power plants. On the other hand, the material requirements of wind turbines are higher than those of most other power plants. Again, stressing the importance of going into a recycling process for those technologies. And we have seen that the energy payback time of wind turbines is less than 1 year, in most cases even only a bit more than half a year. Thank you very much.